Hello, everybody. My name is Kristen Gonzalez-Vega, and once again, you are joining us for AP Physics C, Electricity and Magnetism every day. And I am coming from Frisco, Texas. And I have with me tonight, as always, Roger in Florida.
Hi, everybody. I'm Roger Siegel, and we're coming to you from Sarasota, Florida. This is where I live and teach, and thanks for joining us.
Okay, so we have been talking about capacitance, capacitors the past few days. We wrapped that up yesterday with dielectrics, and today we get to start on circuits. So that is always a really fun topic, circuits. We're going to spend quite a few days on circuits. Today, we're going to do just the kind of basics of what is current, resistance, and voltage or potential difference in a circuit. We're going to talk a little bit about drift velocity, multiple resistors in a circuit, how you treat those, and resistivity. And we're going to do a lab-based question at the end. So lots to get through. Again, my name is Kristen Gonzalez-Vega, and we have Roger also joining us this evening. And we are so happy that you're joining us and watching these. Tonight, we're going to describe the relationship between current, potential difference, and resistance, explain how the properties of a conductor affect resistance, use microscopic definition of current and a conductor, describe the properties of the conductor and the idea of drift velocity, and then describe the relationship between the electric field strength through a conductor and the current density within the conductor. So we're going to start off with just a basic review of what current and voltage really are. Right? So a lot of people get confused about these quantities. They're, abstract and kind of hard to see. But the easiest analogy I like to use is using a post office and mailman analogy. But the short of it is that the voltage or the potential difference in a battery in a circuit is the amount of energy per charge, right? So as those charges are flowing through the circuit, the amount of energy or joules that those charges are carrying. And then the current is the flow of the charge through the circuit. So how much charge per time is passing through one point in our circuit. And our conventional flow of current is positive charges going out the positive terminal of the battery and coming back around the negative terminal of the battery. And that's what we still talk about and use today. A couple other things to know is that not only do we measure the voltage in volts, but we could also measure it in joules per coulomb. And a lot of times we kind of go back and forth with voltage and current and with their kind of alternate units, right? So 1 volt is 1 joule per coulomb and 1 amp is 1 coulomb per second. So kind of using those other units too kind of helps you get through some things. So I'm just going to do a real basic kind of showing you of our circuits, and I'm going to switch over and I've got a FET simulation here. And we're just going to look at a basic circuit that has a battery and 1 light bulb to start. We're going to close the switch and we're going to see that current coming out that positive terminal, going through the light bulb and back and around, right? So obviously we have to have a closed circuit in order for that current to flow. That potential difference within the battery is what's giving that push to those charge to go through the circuit. And that energy that those charges are carrying is being dissipated as light in the light bulb. And those charges go back to the battery. They gain that potential energy as they travel through that potential difference, and round we go. If we were to add another light bulb, let's kind of make predictions. And we're going to do a little bit more detailed circuits later, but let's just get out here my amp meter and my voltmeter, and let's look at what's going on real quick. So I just want to look at what is the current going into that light bulb, right? So if we look at the current, it's 0.9 amps. If I look everywhere, what is it? 0.9, 0.9, 0.9. Well, let's also look at the potential difference. Let's look at the potential difference across the battery from one terminal to the other. That's 9 volts. Let's look at the potential difference across our light bulb. Also 9 volts, right? Okay. So if I were to just real quickly here, let's open this back up. Let's cut this open. Let's add in one more light bulb. All right, and let's close this again. So if we look now at the current, what do you think is going to happen if I measure that current? It's 0.45 amps before this light bulb, after that light bulb, after this light bulb. Everywhere it is. Let's look at the potential difference across the battery. It's still 9 volts. If I go across this one light bulb, there we go, 4.5, and across this one, also 4.5. So some things to be thinking about here as we're talking about circuits. And I also want you to kind of notice how I was measuring those. And this really is not this is more of, for the current, is more of like a tool that's not really how we would measure the current, but we're going to talk about how we measure those things tonight. So let's go back here to the PowerPoint and keep on trucking along. Okay, so we've got that current and that voltage and what those are. And then we also have resistance within our circuit, right? So the resistance is what kind of is restricting or resisting that flow of the current in the circuit. So it depends on the material and the shape of the resistor. Our equation that we use is that the resistance is equal to rho times L over A, where rho is the resistivity of the material. So the different materials have different resistivities. So if you want a good wire for your circuit, right? We don't want our wires in our circuit to have a lot of resistance. So if we want to make a wire, what do we want, a high resistivity or a low resistivity material? Well, if we want our resistance to be low, we want our resistivity of our material to be low. Right? And then we can relate all these quantities together with Ohm's law. And Ohm's law is that the potential difference is equal to the current times the resistance. We can look at that as the circuit as a whole. We can look at each individual elements, and we can apply Ohm's law everywhere in our circuit. The other thing I wanted to touch on tonight, which might not be a review for you, is drift velocity. So if we look at, I'm going to draw here a wire. So here we have a conductor. Maybe it's a piece of wire, right? Copper wire. But I want to look at, let's say, and it's connected to a battery. But if I just have a piece of copper wire not connected to a battery, there are still charge carriers within that material. And they're going to be bouncing kind of all around within that. Now, if we apply a potential difference to that wire, then that's going to push those charges through the circuit. But they're still not like nicely traveling straight through from one side to another, right? They're still bouncing around as they go through the circuit. And so the drift velocity is kind of that velocity as they move through. So they're still bouncing up and down, but they're traveling along through the wire as they go. And what way we can find that or relate that drift velocity is that the current in the wire is equal to N, which is the charge carriers per volume in your conductor, times E, that charge of an electron, times that drift velocity times the cross-sectional area of your wire. Right, so that's a formula that's on your formula chart that can be useful to find that drift velocity. Or if you know the drift velocity, to find the current. What really kind of stands out here though, is that a lot of people, a big misconception that people have is that when you turn on a light switch and that light comes on right away, it's because those charges are moving at the speed of light and lighting the light bulb. And that's not really what happens. So we have all of these charge carriers in this wire. And when we have that current, well, that's creating a domino effect. So we have one charge that's going around that's going to transfer and propagate that current through the wire, and that propagation happens at near the speed of light, but it's not those individual charges that are moving at the speed of light. So we can kind of compare this to a wave. And when you have, let's say, a transverse wave, and the matter within that wave or those molecules are vibrating up and down, right? Think about the wave in the stadium, right? I'm going to stand up, I'm going to sit back down, but the wave is transferring through the stadium. I'm not running physically around a stadium to make the wave, but the wave goes around really fast because the people have that domino effect to transfer the wave. The same thing happens within our circuit, is that those charges create that domino effect, which are lighting that light bulb, and it's not one charge moving right through that circuit. And then the other thing we can talk about with current is the current density. Right? So the current density, which is J, is the current per cross-sectional area that flows through a surface. So we can have different wires of different cross-sectional areas. But if this were, let's say, part of one circuit, what would have to be the same throughout this whole thing? Well, if these are in series with each other, the current has to be the same. But if you change that cross-sectional area of your wire, you're changing the current density. So the electric field inside that conductor is providing the force to move those charges through. So we can relate that electric field and that current density. So this is what you get on the formula chart. But it's good to know where that comes from, but also to be able to go back and forth to Ohm's law and relate the resistivity, right? So the electric field is equal to the resistivity of your material times that current density. But we want to be able to go back and forth between the two. So if we start with Ohm's law and V equals IR, well, how can we relate potential difference and electric field? We've been talking about that a lot, right? We know that the electric field, right up here out of the way, was equal to that change in that potential difference over the change in position, right? So if we're talking the length of the wire, then I can say that the V is equal to the electric field times the length of the wire times the current. Well, I can plug in for resistance. We had that equation earlier here that the resistance is equal to the resistivity times the length over that cross-sectional area. So if I plug that in, that R is equal to the resistivity times L over A. Well, what can we do with the length in the equation? We can cancel that out. And I can say that I over A, that's the current per area, that is J. So then E simplifies down to the resistivity times the current density. So what happens when we have this junction here, when we have this wire that's going from one cross section to the next, is that we get a buildup of charge at that junction. And we can find what that charge is by using Gauss's law, because we have a relationship for the electric field with Gauss's law. So let's walk through that together. If I have here two wires, one with a cross-sectional area, A1, and then a bigger one with a cross-sectional area of A2, and I have this current, I, going through the wire, how can we find what charge is built up here? Well, we can look at the charge building up here. We can look at Gauss's law. So let's still review Gauss's law, right? The integral of E dot dA equals Q enclosed over epsilon naught. I kind of write it in a line here so we can go down. Okay, well, if we look at the junction here, what we want to look at is what is the change really in flux of those two. So remember, each side of these is flux. So if I turn this into E2, that's the bigger surface area, right? Times A2 minus E1 times A1, right? Let's find that difference in the flux of the surfaces. That's going to equal that Q that's going to build up at the junction over epsilon naught. And then we can say, well, what is E equal to? E is equal to the resistivity times the current density. So we can say this would be ρ2 times J2 times A2 minus ρ1 times J1 times A1 equals that charge buildup at the junction over epsilon naught. Okay, but what is, if we go back to our current density, J is equal to I over A. Well, here I've got J times A. So what's J times A? Well, that's going to be the current there. So I can say this is rho 2 I2 minus rho 1 I1 equals Q over epsilon naught. But can we have a different current in these two? No, it's the same current going through both of these. So I1 and I2 are really the same. So I can say this is the I going through that conductor times the difference in the resistivities over epsilon naught, times epsilon naught, is going to give us what that charge is that will build up at the junction. Okay, so both of these topics, both drift velocity and current density, are very small topics. It's not commonly seen within the E&M and the exam, but just it's still on the objectives. There's still something that we want to go over with you. Okay, but back to kind of the basics in the circuit. How do we measure the voltage and the current in the circuit? Because knowing how we measure that is really important. So if we have a circuit, let's say we have a battery. We're just going to keep it simple with one resistor in it. Okay, if I wanted to know what the potential difference was across that resistor, then how would I measure that? We always want to measure potential difference in parallel. Okay, I'm going to draw here so we can see that better. Why do we want to measure? And the way that we symbolize that is a circle with a V in the middle. So any of those circles are where to tell us our meters. So the voltmeter is a circle with a V in it. Why do I want to measure it in parallel? And what should the resistance, what's the I, if we're using an ideal meter, what should the resistance of an ideal voltmeter be? Okay, well, if we look at Ohm's law, and we'll get a little bit more into the loop and junction rule tomorrow, but as we go around in one loop or one path in a circuit, well, if this is, let's say, a 5-volt battery, if I'm gaining 5 volts across my battery, well, I have to lose 5 volts throughout the circuit before I get back to the battery. So if we go around in one loop, voltage is always the same in parallel. So we measure that voltage in parallel because the potential difference across the meter should be the same as the potential difference across our resistor. But what should the resistance of this meter be? Should it be really high or really low? Well, we don't really want the current traveling through that meter, right? So because then the current is splitting and we have less current going through our resistor than what we really have if we didn't have our meter there. So we want the resistance in a voltmeter to be really, really high so that all of that current is still traveling just through the resistor. Okay, so we're measure voltage in parallel, and an ideal voltmeter has a really very, very high resistance. Okay, if we look at this now instead and say, well, I want to know what the current through that resistor is. How are we going to measure the current here? Well, if I put the amp meter, so an amp meter is what measures current, right? If I put an amp meter in parallel with that, now that would create another path for the current to flow. So some of our current would go through resistor and some of it would go through the meter. That's not really telling us what's going through just the resistor. So we always have to measure current in series. It could be before, oops, that deleted my whole line. It could be before, or it could be after, but we're always going to measure the current, which is a circle with an A in it, in series. Now, do we want the resistance of the amp meter to be really high or really low? Well, that we want to be really low. We want the resistance of our amp meter to be pretty much 0, because otherwise we're increasing the resistance of our whole circuit, which again is going to decrease the resistance or decrease the current that's actually going through my resistor. So we measure current in series, and ideally, an ideal ammeter has a very low resistance. Okay, and if we have multiple resistors in a circuit, we need to know how we can combine them to find the total resistance of our circuit. Usually we do that because we want to know what the total current being delivered from the battery is. And so let's look at two different ways, right? So here we have a series circuit. How do we know it's a series circuit? Because if my current goes through one resistor, it has to go through the other resistor. It's a one-lane road, nowhere else for that current to go, no junctions, no branches. So if this is a series circuit, if I want to find the total resistance, well, the rule is we add up all the individual resistors. So this total resistance would just be R plus R, or 2R. So as you can see, as you add resistors in series, what happens to the total resistance? It goes up. So adding always increases the total or the equivalent resistance. That's important to remember. Okay, but if we add resistors in parallel, the rule for adding resistors in parallel is it's the inverse rule. So 1 over the total resistance equals the sum of all the inverses of the individuals. So for this one, 1 over R would equal 1 over, let's just call R1 and R2, but they're the same, so we'll just leave it as R. Okay, well, 1 over R plus 1 over R, if we want to find what the total resistance is, well, if we add these together, we get 2 over R, but that's 1 over R, so we have to inverse it at the end, so we get R over 2. If you add resistors in parallel, you are always decreasing the total resistance. So those are things that you want to remember. If you're adding resistors in series, you're always going to increase the total resistance. And if you're adding resistors in parallel, you're always decreasing the total resistance. Okay, so we're going to look at some practice problems here with Roger, and then he's also going to talk to us about if we have non-ideal batteries and what that means.
Okay, great. Well, thanks, Kristen. So yes, we are going to look at some examples to try and get our brains around this crazy thing called physics. And so join me here and let's take a look at this problem. Now, the first problem is a problem about resistivity and remember, and resistance. And so remember, resistance is the current is something inherent in the material that makes it hard for the current to go through. And so we've got two different materials here, two different wires, if you will, and they're the same length. So we've got silver and we've got brass. And I'll tell you right now, silver is one of the lowest resistivities of any material. If you want to make a very, very conductive wire, make it out of silver. And as a matter of fact, during World War II, a lot of the silver in the United States that had been stored in Fort Knox was sent to Oak Ridge, Tennessee to help make the magnets to create the material for the atomic bomb. So that was, all that wire was made into silver. But anyway, I digress. Okay, so we've got silver and brass. And so we've got these two pieces and they've got the same length. So I'm going to draw the same length, but they tell me that the brass is much bigger. It's got 5 times the diameter of the silver. So it's a big old wire. Same length, but really, really fat. Okay, and so this distance here, you know, this is R, or I should say, they talk about diameter. I don't like diameter, but I'll stick with diameter. And so here we have diameter, and here we have 5 times the diameter. Okay, much bigger. And then we know that the resistivity, as I said, the silver is very low, and the resistivity of the brass is 5 times the resistivity of the silver, and but the diameter of the brass is 4 times. I'm sorry, I said 5 here, and that was wrong. I'm confounding my changes. It's 4 times the diameter. So this is going to be 4ds, or 4. We'll put it over here as well. Okay, so this one's much thicker. This one is, but they're the same length. And so we want to compare their resistance. So as Kristen just showed us, there's a formula on your formula sheet for resistance, and that's the resistivity times the length divided by the area. And so let's go ahead and look at each of these. So the resistance of silver is the resistivity of silver times the length over the area of the silver, the cross-sectional area of this wire. That's what we mean when we say the area is the cross-sectional area. And the resistance of the brass is the resistivity of the brass times this length over the area of the brass. Now, I'm going to replace this with 5 rho S times L. And then look in the bottom here. We said that the diameter is 4 times. Well, what does that mean about the cross-sectional area? Well, the relationship between the area and the diameter is square, right? You square the half of the diameter to get the area. And so let's go ahead, and if we're going to have 4 times the diameter, that means we're going to have 16 times the area of the silver. And so you can see that rho S LAS is the same as here, rho S LAS. So RS, resistance of the silver, is 5/16 of the the resistance of the brass, here we go, is 5/16 the resistance of the silver. And so that's what we get there. Okay. All right, next one. Now, coming down here, we talked about, Kristen we were talking about the resistance of resistors in series and in parallel. So let's look at this circuit. So first of all, one of the things that we hope you're going to remember how to do and you'll get better at during this time is figuring out where the circuit is in series and where it's in parallel. And so, sometimes I will tend to draw these in exaggerated ways to kind of show or to attempt to show a little bit better why they're the way they are. Now, I want to remind you of, or tell you about something. These pieces here, these junctions, it's very important when you're doing circuits to be able to use your imagination, because the junctions in and of themselves, it doesn't necessarily matter where they are. For instance, I could put this wire over here instead of over here. And if I did that, if I just got rid of this part of the wire right there and just had it look like that, well, it would still function in that same way as long as we had this joining here. And so this means that we can use our imagination to see what's going on. So I hope you'll see what I mean by this. So watch, I'm going to redraw this. Actually, I'm going to start up here. And here's my battery of 12 volts. And then I'm going to draw this first resistor of 10 ohms. I'm going to draw this second resistor of 10 ohms. And then down here, I'm going to draw this resistor of 12 ohms. And so these are the 3 resistors I've drawn. Please take a look and see. Here's our 10 ohms, okay? 10, 10, and 12. All right, and those are the 3 that I've just drawn. Now, I'm going to draw the rest of the circuit. I'm going to draw now this branch of the circuit, but watch the way I draw it and see if it shows you something. Instead of drawing the junction here, I'm going to put it over here. And now we have 15, 10, and 15. And so what I hope you can see by this is these 3 resistors are in series. We have one after the other, after the other. However, you can see now that they are in parallel only with this one, only with that one. And so that's what I wanted you to see in drawing it that way. So since these 3 are now, we can say, okay, these are definitely in series, right? We go like that. Well, we just add them like this, resistors in series. And so we're going to add 10 plus 15 plus 10 plus 15. 15 ohms plus 10 ohms plus 15 ohms. Okay. And that gives us 30 ohms. I'm sorry, 40 ohms. All right, now what I'm going to do is I'm going to redraw this now. And I've got the 12 volts here, the 10 ohms. I've got these 10 ohms. I've got these 12 ohms, these three. 1, 2, 3, 1, 2, 3. But now I am in parallel with this 40 ohm resistor, or these three resistors that are 40 ohms. Now, what do I do with this? Well, when you have resistors in parallel, we know that 1 over Rp is 1 over R1 plus 1 over R2 plus ... We have to add their inverses and take the inverse. Now, the way I always do this, and I tell students, please use your calculator for this, because when time is of the essence, you don't want to be messing around with fractions. So what I'll do is I'll say we have 10 inverse plus 40 inverse, and that's how we're going to do that problem. Now, I'm a big believer in arithmetic. I think it's good to be strong in arithmetic. So it's good that you can do 1/10 plus 1/40 and take the inverse of that on the paper. And so we have 4/40 plus 1/40 inverse. And so that's going to be the inverse of 5/40, which is going to be 45ths, which is going to be 8. Now that took some time, right? That took a little bit of time. So please, I'd like it if you got better at using your calculators. Okay. And so, please use those calculators that you spend so much money on. And look how easy this is to do. You're going to get really good at just plugging this in super, super fast. And you're going to plug in 10 inverse plus 40 inverse, close parentheses, inverse. And that's how you're going to do it really fast. Because remember, you only have a certain amount of time to answer these questions. And so that's our 8 ohms there. All right, I hope that wasn't too easy for you. All right, good. So now we can see that these two together make 8. So we're almost done. I'm going to go back this way now. You draw a lot of pictures when you do these circuits. And so now we have 10, 8, and 12, all in series. So 10, 8, and 12. This 10, 8, and 12. And remember, 8 was all of these together. That's 8. And so 10 plus 8 plus 12 gives me 30 ohms. And so that's our answer. And that's how you do that problem. Again, you're going to find these get really easy with a little bit of practice, and you're going to find that they're a lot of fun as well. All right. Now, Kristen was telling us about something called internal resistance. And I meant to go grab a battery, but I didn't. But, oh, wait, there's a battery right here. Okay. I knew I had one close by. All right, let's see. Now, I'm going to go ahead and show you this really close. So you guys have seen batteries before. It's not your first rodeo here. Okay, there's our famous battery. Now, if you look at the battery, every battery has on it a voltage. And that voltage for, this is a AA battery, is 1.5 volts. Okay, now that is called the EMF. Electro-Motive Force. We have a special name for that. But that specifically means the amount that the battery is pushing its pressure, its voltage, when it's not doing anything. Okay, this is the, so the EMF that is stamped on the side, this is what is written, stamped on the battery. Okay, that is the unloaded potential difference, or the unloaded voltage. And we say it's unloaded because it's not doing anything. It's not pushing current. We're not loading it up with a job to do, basically. Now, all batteries have this resistance inside of them. It's built into the physical nature of the battery. It's got chemicals in there. This is not a chemistry class, but if you studied chemistry or electrochemistry, you know that it's a complex reaction that's happening in here, and there's always resistance involved. Now, once we start pushing current in this circuit, right, the current starts to go through this circuit. Once that starts to happen, the internal resistance in the battery, notice we draw this tiny little resistor. Now, listen, there's not a little resistor in here. You won't crack it open and find it. The internal resistance we're talking about is about the physical, chemical nature of what's happening in the battery, that it's always there. And so that internal resistance is always there. Most of the problems that we're going to do in AP E&M, AP Physics C E&M, do not have internal resistance. Again, this is kind of a very small concept, or not treated a lot, but once a year we do see a question about internal resistance. So we wanted to make sure you knew about it. So let's look at this. It says ideal batteries, we ignore their internal resistance. And again, 95% of the problems that you do in this class will be ideal batteries. There will be no internal resistance to talk about. But let's look at this problem and see if we can figure out what this one would be like. Now, I'm going to draw this similar to the problem we just saw, and I'm going to draw this little resistor inside. Usually that's denoted with a tiny r. And then I'm going to have this other big resistor. And the reason I have this big resistor is you're not allowed to connect the volts of a battery, the terminals of a battery, without a resistance on them. Otherwise, you will cause a short circuit. Okay, so here's our battery. And remember, there's no little resistor in there. This is just my symbol for it. And so it's a 12-volt battery, the EMF. That's what's stamped on the side of it, all right? And we hook it up to this circuit. And remember, we saw that the ammeter goes in the circuit. It goes in series with the circuit. And this ammeter is reading 0.5 amperes. Now, that means that everywhere in the circuit, the current is 0.5 amperes. 0.5 coulombs per second are going past this point. 0.5 coulombs per second are going around this corner. 0.5 coulombs per second are going here. This is 0.5 coulombs per second everywhere in the circuit. Okay. Oh my gosh, I better speed up. Sorry, going too slow. All right, so now we got to find the, we're going to find the resistance, internal resistance of the battery. Now we know that we've got a 12-volt battery when I don't hook it up to a load, but when I hook it up to the load and I put a voltmeter on here, I see that it says 10 volts. So that means I've got a voltage drop, delta V, of 2 volts in this internal resistor. And since I know the current is the same everywhere, I know that I is equal to V over R. That means that R is equal to V over I. And so then we're going to have 2 volts, that's our potential difference, divided by 0.5 amperes. And that's going to give me 4 ohms. And so notice that's a tiny resistance that's consistent with what we would think in a situation like that. Okay, Kristen, sorry to take too long. All yours.
No, that was fine and very impressive at the end there. So we're going to do one problem today. It's a lab-based problem. There are parts of it we're going to spend a little bit more time on, and parts of it that we're going to kind of go a little bit quicker on, because you might not be asked to actually make a graph this year. You're going to have to analyze a graph, but actually physically drawing and graphing is not going to happen this year. So that part of the question we're going to go a little bit quicker on. But the other parts we're going to really talk about, because there's lots of other good conceptual things going on. All right, so we have a circuit here that is shown consisting of a source of variable EMF, an ideal ammeter A, ideal voltmeter V, a resistor of resistance R, and a sample of wire with resistance R. So a couple of things here. When you see this symbol of the arrow on an element, we see this sometimes with resistors. If you have a resistor that's got an arrow, what that means is it's adjustable or variable, right? So your dimmer switch in your dining room, those are variable resistors. Okay, but this time we have a variable power supply, right? You can adjust the voltage on that. we have a resistor, and then we also have a sample of wire. And really, wires do have resistance, right? Small amount. And so we want to look at this situation. We have an ideal voltmeter and an ideal ammeter. We talked about what that means earlier, right? If we have an ideal ammeter, very low resistance. Ideal voltmeter, very high resistance. So if we look at the first part, A, how does the current through the wire sample compare with the current through the resistor? Take just a second. If we look at the circuit, we want to know, how does the current through our little resistor compare to the current through our resistor? Not necessarily little resistor. We don't know what the resistance of these wires are. It could be a really high resistivity material. But how does the current through the wire compare to the current through our resistor R? And you guys all know this, right? What kind of circuit is this? Remember, this is really just our meters. These are not physically a part of our circuit. So if we're looking at our actual circuit and we're going around the circuit, we can see that this is a series circuit. So what should be true about the current in both of those? They should be the same. Okay, how would we justify our answer? We will justify our answer by saying that the circuit is a series circuit. And what does that mean? That the current is the same everywhere in that circuit. Okay, but what about the potential difference? How does the potential difference across our resistor compare to the potential difference across our wire sample? So is the potential greater across the resistor? Is it greater across the wire sample? Is it the same in both? Or does it depend on the resistance of the sample? Well, if we're using Ohm's law and we want to know the potential difference across either one of those, and the current is the same, then what does the voltage drop depend on? It depends on the resistance. So, which resistance depends on the resistivity. So we don't necessarily know if it's going to be greater through the wire sample or greater through the resistor, because it depends on the resistivity of the wire. If the wire has a very low resistivity, then we could say that it would be greater through resistor. But if it has a greater one, that it could be greater through the wire. We don't know. Okay. Next part, with the sample of wire in place, the EMF of the source is set to a given value, and the current through and potential difference across the resistor R are measured. This is repeated for several trials of EMF, and the data are recorded in the table below. All right. So we're going to change the voltage on our power supply, and we're going to measure the potential difference across the resistor, and we're going to measure the current in the circuit. Okay. So we've got, what do we want to graph in order to be able to determine what the resistance of the wire sample is? So this is one of those where we're trying to figure out, what are we going to graph to get something else? So what do we have to do? We have to come up with a relationship. We have to come up with an equation. Always when you're trying to graph something, you got to start with your equation. So what would be an equation that we would use for this situation? Well, if we go back here, and again, we're going to talk a little bit more about loop and junction rules and Kirchhoff's laws tomorrow. But if we look at the circuit, and if we take these as two separate elements and they're in series, well, we know that potential gains should equal our potential losses. So we're gaining across the battery, but we're losing potential. We have a potential difference drop across our resistor here, and we also will have a potential difference across the resistance of our wire. Right? So we have two losses and we have one gain. So if I were to write an equation, well, I would say, well, the EMF of the battery has to equal the voltage drop across my resistor big R plus my voltage drop across my little r. Okay, so if we know what the voltage drop across our big R is, and we know what the potential difference of the battery is, or the EMF of the battery, then really I could say, well, the EMF of the battery minus that potential difference across my big resistor will equal the potential difference across my little resistor. And what can we plug in for there? We can plug in Ohm's law. And we can say that it's the current through times that resistance of the wire. So this is kind of what we call our working equation, right? This is what I'm going to look at on what I want to graph. So we identify what are variables, what are constants, right? So the EMF, well, that's variable. The resistance, that's a constant. That voltage drop across my other resistor, that's a variable too. And my current is a variable, right? So really we've got kind of three variables here. But if we're going to solve and we want to know R, well, then let's just bring my current over and say that the EMF minus VR over I is going to equal little r. So whatever's on top of my equation is what I'm graphing on the y, whatever on the bottom is what I'm graphing on the x, whatever's left on the right side is my slope. Okay, because we've got y over x always equals slope. So what would we graph on the vertical? We'd graph the EMF minus that voltage drop across the resistor. And on the x, I would graph my current through the circuit. Okay, so horizontal is going to be current, and vertical is going to be the EMF minus that voltage drop. And then it's nice if I do it that way, because if I were to graph it, that should be a straight line. And the slope of that is going to be what? R, because that's the only thing that was left on the right side of my equation. Okay, so we won't take time to do that because you won't be asked to do that on the exam, and just for time's sake, because I really want to talk about this last part. If we graphed it and found the slope is our resistance. We could use that to get the resistivity, because resistance is equal to resistivity times length over that cross-sectional area. So this is the slope, right? They're giving you the length of the sample. They give you the radius. And so we can use that radius to get the area. Okay, but G is what I really want to focus on, and I want you to take a second to really think about, because this is something that I could predict and would probably bet a lot of money that would be something that it would be really good to ask, because this is always what we like to ask on the experimental type questions is, what happens if your results are not what you expect? What does that mean? Can you reason through what happened, right? What assumptions are you making in your experiment, where if something changed, what does that mean? Okay, so in part GI, suppose the ammeter used to collect the data was not ideal. Would the actual value of the resistance of the wire sample be greater than, less than, or equal to that calculated in part E? So I'm gonna give you a minute. I want you to think about, what does that mean? What would that change? And would our actual value of the resistance of the sample be greater than, less than, or equal to what we just calculated? Okay, what are our predictions? So what would that change? Let's think it through and reason through it. If our ammeter is not ideal, what does that mean? That means our ammeter has resistance. So this ammeter would have its own resistance. So what would that do to the total resistance in the circuit? Well, what that means is, what I used to just be saying, the resistance that I calculated was just the wire. Now I really have that resistance being the R of the wire plus the R of the meter. Okay, so what does that mean the actual resistance of my wire was? Well, it's got to be less than what we just calculated, because we were taking everything, all of that resistance, as being from the wire, but some of it's actually coming from the meter, so the resistance of my wire has got to be a little bit less. Okay, and now what if instead our voltmeter is replaced by a voltmeter that is not ideal, and the experiment is repeated? Would the readings of the ideal ammeter, right? So I'm going back now, so my ammeter is now ideal again, but my voltmeter is not ideal. So would the current reading through my ammeter be greater than, less than, or equal to that than we had before when this was ideal, right? So would changing out that meter for a non-ideal meter increase my current in my circuit, decrease my current in the circuit, or keep it the same? So again, think about that for a second. What would that change and what would that mean? Okay, if you want some more time, pause it. Let's discuss. Well, our ideal meter has a resistance essentially of infinity, right? But now it is not infinity anymore. So now this has some resistance that is not infinity. So if we put in another resistor here in parallel with this resistor, what does that do to the equivalent resistance in my circuit? What did we say earlier? If you add resistors in parallel, the total resistance in our circuit goes down. So by adding that resistor of the voltmeter in parallel with our resistor R, we're going to decrease that equivalent resistance. But without changing the EMF, if I decrease resistance, what happens to the current in my circuit? It's going to go up according to Ohm's law. If resistance goes down, current's going to go up for that same potential difference. So we're going to have a greater current now through my ammeter because I've decreased the resistance of my circuit by adding in that non-ideal meter in parallel with the other. Okay, so I really want you to think about these, and if you want, redo them, take more time to think about it, make sure that makes sense, because this I think is something that's really, really important, a skill that you need to have, especially this year. Okay, that is all we have for today. So we should be able to talk about what resistance, voltage, and current is, be able to find resistivity or resistance, know about drift velocity, and about current density. So tomorrow, Roger, what are we going to do?
Tomorrow, we're going to start doing some slightly more complex circuits. We're going to start to look at finding the current in each branch of the circuit and the voltage drop across each part, across each resistor.
Awesome. I love doing that. It's like puzzles, like doing a Sudoku puzzle. Okay, well, tune in for that tomorrow, and you guys have a wonderful night.